Hi everyone, happy Monday. I hope you had a great weekend. Today we are moving on. You should have your notes packet out and we're going to go over how to determine if a molecule is polar or not. So Friday we went over the different types of bonds. There are ionic bonds, which is when the electronegativity difference is greater than 1.7 between atoms. And you don't ever have to memorize any electronegativity values. I'll always give those to you, and you have them in your notes packet. The less electronegative atom, which is your metal, actually gives the more electronegative atom its electrons, which is your nonmetal. Our metal becomes completely or fully positive. The nonmetal becomes completely or fully negative. There are full charges on an ionic bond. While a polar covalent bond is when the electronegativity difference is between 0.4 and 1.7, and electrons are not shared equally. Because they're not shared equally, that means the electrons in the bond, they stay closer to the more electronegative atom, making that partially negative, while the less electronegative atom is left partially positive. And then we have nonpolar covalent bonds, where the electronegativity difference is between 0 and 0.4, which means electrons are being shared equally between the two atoms, and there is no charge, partial or full, on either atom in a nonpolar covalent bond. So 3 types of bonds, and it really comes down to the electronegativity difference. Now, once you determine what type of bond it is, if it's a polar bond, we have to draw charges on it, but that's only for polar bonds, not nonpolar. And so below I have the Lewis structure for CO2. It's already drawn to save time. If I go to my electronegativity value table, carbon has an electronegativity value of 2.5. Oxygen has an electronegativity value of 3.5. That's supposed to be a decimal. Oops. So this is a polar bond, and this is a polar bond. And when the bond is polar, we have to draw symbols that signify it's a polar bond and where the charge is. You have arrows and the little symbols. We'll do arrows first. Because oxygen is more electronegative, the arrow points to the O. So there and over here. Now, that being a double bond, doesn't change anything, you don't do anything weird. That's all we would do. So that or those little symbols. Again, oxygen's more electronegative, so it gets the partial negative, and carbon gets the partial positive. And so that's how we draw the charges for CO2. So this has 2 polar bonds. If I were to do this for, here's a new structure, CH3Cl. So we've got 2 types of bonds here. We've got a carbon and a chlorine bond, and then we have a carbon and a hydrogen bond. And there are 3 of those. So different types of bonds to think about this time. So looking at the carbon and the chlorine bond. Carbon's electronegativity value is 2.5. Chlorine's is 3.0. So that's a polar bond. Chlorine is more electronegative, so I'll draw the arrow towards chlorine. Perfect. Now, looking at the carbon and the hydrogen bonds. Carbon 2.5, hydrogen 2.1. That is 0.4000. It is a nonpolar bond. And so we don't draw any symbols on the CH. Just leave it as it is. And that's okay. You might have a molecule with 3 polar bonds and 1 nonpolar. They don't all have to be the same thing in the compound. So I can have my arrow, or if I wanted to get rid of that and draw the symbols, partial negative here, partial positive here on the carbon, and just leave the H's alone. So now, moving on. How do we figure out if a molecule is polar or not? So we have polar bonds. a bond in which electrons are not shared equally, and there's a partial charge on both atoms in the bond. We also have polar molecules. A polar molecule is a molecule that has overall charges on it. So the molecule in general has a charge because the bond's dipoles or the bond's charges do not cancel out. And something important, star this, circle it. Just because a molecule has a polar bond does not mean it will be a polar molecule. There's a big difference between that. So, in your notes, if you flip past where we were last, this is what you should see, and we're going to go through this together, paragraph by paragraph. So, how do I determine if a molecule is polar or not? When there are no polar bonds in the molecule, that means there's no permanent charge difference between one part of the molecule and another part because they're sharing electrons equally, so the molecule is nonpolar. No polar bonds, not a polar molecule. Seems pretty simple. Underneath, I've got the Lewis structure for Cl2. It has no polar bonds because it's chlorine. They have the same electronegativity difference, so it's a nonpolar molecule. Now, a molecule can have polar bonds and still be nonpolar. If the polar bonds are symmetrical or evenly distributed, the bond dipoles cancel out. The bond's charges cancel out, and so the molecule is nonpolar. For example, for BF3, it's a trigonal planar, it looks like this. All of these bonds are polar. That's why the symbols are drawn here. But because they are symmetrically arranged around the central atom, no one side of the molecule is more negative or more positive than the other. And so overall, this molecule is nonpolar. There's not an overall charge on it because all of these charges cancel out. That's also the case with carbon dioxide. CO2, we looked at it a minute ago. It has polar bonds, partial negative, partial positive, partial negative, but because it's symmetrical, these negatives cancel out. And so this is a nonpolar molecule. This end of the molecule is negative, the right end of the molecule is negative. There's not a more negative or a more positive side of the molecule. They're both negative ends, so it's nonpolar. You might be confused right now. That's okay. I kind of have an easier way of understanding in a few minutes. Okay, continuing on. So below, I've got the Lewis structure for water. Water is bent, oxygen's partially negative, hydrogens are partially positive. And this is a polar molecule. Water is polar. One, because the OH bond is polar, is a very polar bond. And then two, this bent geometry makes the polar bonds uneven or not symmetrical. When I look at this structure, it's really like a triangle. There are three sides. The hydrogen up here is partially positive, partially negative. It's not symmetrical. That's why it's a polar molecule. The difference being for when it was that BF3, it was partial negative, partial negative, partial negative. It all canceled out. That's not the case with water. Water, there is a positive side and there is a negative side. And overall, this molecule has a charge. So, just because something has polar bonds does not mean it's a polar molecule. When it is not symmetrical or the bonds don't cancel out, it's polar. And you might be really confused, so these steps are pretty much like key for determining if it's polar or not. Star these, know these, highlight these. So, and this is what I want you to follow. So first, we're going to identify if the bonds in the Lewis structure are polar or nonpolar by electronegativity difference. Step 2, if there are no polar bonds, the molecule's not polar. Makes sense? Step 3, if it has polar bonds, then the molecule can be polar or nonpolar. If there are no lone pairs on the central atom, and if all of the atoms bonded to the central atom are the same, the molecule is nonpolar, even though it has polar bonds. Or if the central atom has lone pairs on it, or has at least one polar bond with different atoms bonded to the center, the molecule is polar. And so what do I mean by all atoms bonded to the center are the same? That would be like carbon, hydrogen, 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 like that. Versus if it says different atoms bonded to the center, that would be like carbon, hydrogen, chlorine, chlorine, oxygen. Or that could even be a hydrogen down there. It doesn't really matter, but the carbon's bonded to hydrogen and it's bonded to chlorine. So that would be an example of a polar molecule, while this CH4 over here would be nonpolar. So these steps, extremely important, and this is how we're going to figure out what molecules are. And we're going to do the practice at the bottom of your practice packet. So first, OF2. And there really should be a step 0. We need to draw the Lewis structure. That's really step 0, the first thing we have to do. So OF2, oxygen has 6 valence electrons, fluorine has 7, and there are 2 of them. Total, that's 20 electrons, 10 pairs. Okay, oxygen goes in the center, fluorine around it. It's 2 pairs, 3, 4, 5, 6, 7, 8, 9, 10. Now every atom has 8. I've used all my 10 pairs. My Lewis structure is just about good. The shape is not correct, and shapes for polarity actually end up being very important. My center atom has 2 lone pairs on it and then 2 things attached. So this has bent geometry, and I need to draw it bent. So I'm going to erase this and redraw it. Correct. Okay. Okay, so now I've had my Lewis structure drawn. Let's do step 1 now. Identify each bond in the Lewis structure as polar or nonpolar. I'd go in my notes, flip over to the table of electronegativity values. Oxygen is 3.5, fluorine is 4.0, so that difference is 0.5, so that is 2 polar bonds. And then I need to draw the symbols onto my Lewis structure. Fluorine's the more electronegative one, the value of 4.0, so my arrows point towards the F. And hopefully looking at this, I hope you can see, does it look symmetrical? Are those negative or polar bonds canceling each other out? If the answer is yes, it's nonpolar. If the answer is no, it's polar. Or let's go through our steps. So if there are no polar bonds, that's not the case. There's polar bonds. So my molecule has polar bonds, step 3. Okay, 3A. If there are no lone pairs on the central atom, well, my center atom has lone pairs. So B, central atom has lone pairs. The molecule is polar, which this is, it's a polar molecule. And I know that because it's got a polar bond and my center atom has lone pairs. I didn't even have to read the rest of A because there were lone pairs on it, so it's a polar molecule. Okay, next example. So first, let's draw the Lewis structure for CCl4. Carbon has 4 valence electrons, fluorine has 7, and there are 4 of them. That's 28, 28 plus 4, 32 electrons, or 16 pairs. So carbon in the center. I've used 4 pairs, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I've used all 16 pairs. Everything has 8 electrons. My Lewis structure is correct. Okay, so let's look at step 1. Identify each bond in the Lewis structure as polar or nonpolar. I go to my table. Carbon has an electronegativity value of 2.5, chlorine 3.0, so these are polar bonds. Chlorine's the more electronegative one, so I'll draw my symbol with the arrows pointing towards chlorine. Okay, so my molecule has polar bonds. It can be polar or not polar. Let's look at A. If there are no lone pairs on the central atom, well, there's not any lone pairs on my central atom, it's only got bonds, so that's true. And if all of the atoms bonded to the central atom are the same. Well, in this case, carbon's only bonded to chlorine. It's all chlorine around it, so that's true. The molecule is nonpolar. So this is a nonpolar molecule because my center atom does not have any lone pairs and all of the atoms bonded to the center atom are the same thing. They're all chlorine. Also, looking at it, this and this cancel out, this and this cancel out. All of the polar bonds cancel out from each other. It's symmetrical. It's a nonpolar molecule. Depending on the person, you might want to follow these steps to figure out if it's polar or not, or by drawing the Lewis structure. Some people, you might not even have to think about these steps. Once you draw your arrows or your partial negatives, you can see do they cancel or not. If the answer is yes, then it's nonpolar. Okay, and one more example, O2. Well, let's draw the Lewis structure. Oxygen has 6 valence electrons, 2 of them, so that's 12 electrons, 6 pairs. O and O, that's 1 pair, 2, 3, 4, 5, 6. Now, this is not the correct Lewis structure because oxygen over here on the right is not content, so I have to erase one because it only has 6, make a double bond. So here's the Lewis structure. Okay, step 1, done. Step 2, or really step 1, identify each bond in the Lewis structure as polar or nonpolar. Well, they're both oxygen. They both have an electronegativity value of 3.5. So those are nonpolar bonds. They share electrons evenly. And because they share electrons evenly, there are no polar bonds. So it's a nonpolar molecule. We don't have to think about it, really. There's no charge because everything's being shared evenly amongst that oxygen. In your notes packet on the next page, from where you wrote down those examples, I made a table or a flow chart front and back. If you follow this flow chart, it will help you figure out if something is polar or not polar, but you have to follow the flow chart. And I have examples drawn in there for you. So that's a good summary for you to reference. And why do we care if molecules are polar or not? Well, the fact that a molecule is polar or nonpolar determine how it exists and functions. Water is polar. How much of us is water? How much of all living things are water? How much of our earth is water? If it was nonpolar, earth, life, nothing would exist as we know it. And then if you like biology, if you like biology and think you will be taking or having chem again, think again. If you're bored I linked some Khan Academy articles about cell membranes because our cell membranes have polar parts and nonpolar parts. Remember we learned hydrophobic, hydrophilic. Hydrophobic is the nonpolar, hydrophilic is the polar part of it. If our cell membranes were flipped and the outside was nonpolar, we wouldn't be able to function right. Transport proteins in our cell membrane, they let stuff go in and out of the cell. Well, guess what? We need polar things to go into our cell. We need polar transport proteins. And so a lot of our cell function is determined by if something's polar or non-polar. Awesome. I hope you enjoyed this lecture. You do have a quiz to go take on Canvas now, and I will talk to you all later. Please message me with any questions you have.